Okay, so today we are going to look at our second discrete time model of species interactions. Most of the stuff that we're doing is in continuous time, but it's good to know that there are some discrete time models as well, and that these have some similar properties, but also some slightly different ones. We saw a predator-prey model last week, which exhibited some chaos, which we don't see that kind of chaos in a continuous time model with two species. Interestingly, when you have like 3 or more species, you can get chaos in continuous time. Today we're going to be talking about a host-parasitoid model. This is another very famous model in mathematical biology called the Nicholson-Bailey model. Has anyone heard of parasitoids before? Yeah, okay. So parasitoids are in some ways partway between a predator and a parasite in terms of the effects that they have on their hosts. Predators obviously have to kill their hosts. Parasites can kill their hosts, but they can also reproduce within them before that happens. Whereas a parasitoid is, say, something like certain parasitic wasps that lay eggs in other organisms, and those eggs hatch and kill the organism. So there's kind of a little bit of both in some ways. The face huggers from Alien. Has anyone seen? Just checking there's not like a big generational divide here. So yeah, face huggers from Alien are a classic example of parasitoids. Okay, so they don't eat their hosts, but they lay eggs in them, and then they kill the hosts when they are born. Okay, so today we're going to be talking about this host-parasitoid model. It's in discrete time. This is known as the Nicholson-Bailey model. We'll cover things called like searching efficiency. That's kind of similar to our attack rates that we've looked at before. We'll also talk briefly about some of the Poisson process. Who's heard of a Poisson process before? Yeah, okay. This is essentially understanding, we use this to understand how many hosts are infected in a given time unit, okay? Okay, so last time we met the general form of a discrete time predator-prey model, or a discrete time model of species interactions in general, which is of this form here. T plus 1 is equal to xt plus some function f of xt yt, where f is giving you the change in species x, and then yt similarly with its own updating function. And we can write these alternatively as just f of xt yt, some other slightly different function. They're both equivalent, right? We can either write them in this form or this form. And we can do things like find equilibria by setting x star is equal to, in this case, I'll set it to the tilde one, f of x star, y star. Likewise, y star is equal to g tilde of x star, y star. Or alternatively, these ones here would be equal to 0. So left and right hand sides balance, those are to find our equilibria. And then we can use the jury conditions, these 3 inequalities here, by looking at our Jacobian, analyzed at each of our equilibria, and then compare the trace and the determinant. And if these 3 inequalities are satisfied, then that means that our eigenvalues have absolute value less than 1. And because our solutions in discrete time always will have something of the form lambda to the t in them, this ensures stability. We compare that to a discrete time model, continuous time model, where our solutions are of the form e to the lambda t. Here you need to have the real part of lambda to be negative, for this to tend to 0, whereas here, if lambda is less than 1, then this will tend to 0, the absolute value. So this continuous time is the discrete time version, okay? Just make sure, just like in single population models, there's a distinction in terms of where the boundary is. And so these jury conditions are just ensuring that that the eigenvalues have absolute value less than 1. Okay, so we're going to explore this model of host-parasitoid interactions, just a little bit more about what host-parasitoids are. So it's an organism that has young that develop on or within another organism. So this is an example of a parasitic wasp laying its eggs inside this larvae here. As I said at the start, these parasitoids have characteristics of both predators and parasites in the sense that they always end up killing their hosts. So they're kind of like predators in the sense they always kill their prey and also feeding off those resources. Arguably, parasites are just like mini predators. Depending on the organisms, the boundary between predators and parasites can become a bit blurred, and parasitoids definitely kind of are ones that sort of blur that boundary. Viruses can infect bacteria, so there are viruses called bacteriophages, which infect bacteria. They are pathogens, parasites, but they also in some ways can behave a little bit like predators or parasitoids. They are obligate killers of their host in order to spread. Okay, so they're typically much smaller than their hosts. That's one of the distinctions. Usually predators are bigger or of a similar order of magnitude to their hosts. Parasitoids can be a lot smaller, and they can often have much faster life cycles. Okay, so general host parasitoid model forms something like this here. So if we have our hosts in time step t+1, we tend to think of this as about generations. So in the next generation. Well, suppose we've got some intrinsic growth rate for our host population. Our hosts, the density time t, our host density is h sub t. We have some intrinsic per capita growth rate in the absence of parasitoids. We're going to assume that R is always greater than 1. If R is less than 1, this population is going to die out with or without parasitoids, and that's kind of boring. So we're going to assume that the population, I'm going to put greater than or equal to here technically. We're going to assume that it's always going to be able to spread. If we've got parasitoids in there, we can actually reduce this back down to this strict inequality here. So R is greater than 1 here. That ensures that our population will be growing exponentially in the absence of parasitoids. And then we're going to multiply this by function f, which is a function of both h and p, where p is our parasitoid density at time t. And this is the fraction of hosts that are not parasitized. So what we're saying here is we're saying, okay, the hosts are going to be reproducing, but the ones that are parasitized are going to die. And the ones that are not parasitized are the ones that are going to be able to either survive or they can contribute to the next generation. So that's for our hosts. And then for our parasitoids, their density is going to be C, where C is the average number of eggs that are laid and survive into the next generation. So some of those might die, but we're thinking about the ones that are surviving. Times by the number of hosts in that generation. And then times by the number of hosts, or sorry, the fraction of hosts, I should say, that are parasitized. So here, kind of set up, it seems a little bit round the wrong way. F is the fraction of hosts not parasitized, and 1 minus F is the fraction of hosts that are parasitized. Okay, so fraction of hosts that are parasitized, total number of hosts, and eggs per host. That will give you the number of parasitoids in the next generation. Here, hosts that essentially are not killed by the parasitoid, and also a growth rate for those hosts. Okay, so that's the very general form of a host parasitoid model. A specific one is known as the Nicholson-Bailey model, and this is a classic model. It comes from the 1930s. So really when mathematical biology was still very much in its infancy. And one of the reasons as well that it would be in discrete time rather than continuous time is because they didn't have computers that have nice ODE solvers back then. It's a little bit easier to propagate forward these discrete time models by hand. Okay, so what are the key assumptions of this model? Well, it assumes that these encounters between these hosts and parasitoids follow a linear or Holling type 1 response. So it's based just on the density of those hosts and parasitoids, as well as some searching efficiency, which we'll talk about in a moment. We're assuming that they occur random and independently. These populations are well mixed. There's no kind of clustering or anything going on. It also means that parasitoids are unable to distinguish between hosts that have already been infected or parasitized and those that have not. So with these assumptions here, we can write down the total number of encounters in a time step as some parameter A times by the density of hosts times by the density of parasitoids. So we'll talk a bit more as, we've already met functions of this form already. We'll talk a little bit more about this as well when we go into disease models, starting from Friday. Really what this is kind of saying is, this is known as the law of mass action. And you can think of there being some kind of unit area. And let's put down some hosts, these green blobs, and then some parasitoids. And the same principle applies when we're doing our predator-prey models as well. We haven't really talked about where this actually comes from, though. You can think of these as being like gas particles. They're just kind of moving randomly around this area. We said here that they're moving randomly. Things well mixed, so they're just kind of moving all over the place here. And then they come into contact with each other. Suppose these two are close enough to consider them coming into contact. Well, the law of mass action tells us that the rate at which this happens depends on the rate at which they're moving about. You can think of that as your A parameter. If A is far larger, that means that they're moving around quicker and they're going to come into contact with each other more. And then the density of each of those two things. So if we multiply these together, we end up with the rate at which the red dots come into contact with the green dots. And that's essentially what we're doing whenever we're using this law of mass action. Okay, so if this is our total number of encounters in a time step, the average for any given host, we call this little n, is just going to be the total divided by the number of hosts, which is just A times by PT. So for any given host, any given green dot here, the average number of encounters that it should, with this parasitoid that it should experience is A, which is the searching efficiency of this parasitoid, how quickly it's moving around, how quickly it's trying to find its hosts, times by the density of those parasitoids. There's the average number per host. What we want to think about is the actual number, not just the average number. We can describe this by something called a Poisson process. And this Poisson process is telling us how many events occur in a given time period, given that those events occur independently, randomly, and at a constant rate. Okay, so this is a very nice process that's often used in mathematical biology. Like I said, we're going to talk about infectious diseases, and the same kind of principles apply there. If you're assuming everyone's moving around randomly, what's the time till your next infection event can be described ultimately by a Poisson process, or the number of infection events that you get in a given time period. So what does this look like? Well, a Poisson distribution with probability Pi is telling us a host experiences I encounters with a parasitoid within a time step. So the probability of I encounters in a time step, if we follow this Poisson distribution, this is not something I'm going to test you on knowing, but if you look at a Poisson distribution, if n is our average number, and we want I, we take n to the power of I, times it by e to the minus n, and divide it by I factorial. Okay, this is just something from the Poisson distribution. You're not going to get tested on memorizing this. Okay, if you need it, for example, in an exam, I would give you this. Okay. So that comes from a Poisson distribution is telling us the probability of having, say, 0 or 1 or 2 or 3 or 4 or 5 or however many encounters with a parasitoid, with parasitoids in general, for a given host in this population in a given time step. Okay. Now, if we're assuming that hosts are not able to resist their parasitoids at all, so if they come into contact with them, they're going to get infected. There's no sort of probability then that they are going to be able to resist infection. Then we only care about the first encounter. So as soon as they get encountered by, facehugger from Alien, they're done. It doesn't matter if they were then to come into contact with another facehugger. They've already been infected, right? They've already been parasitized. For those who came in late, sorry, parasitoids And the movie Alien, there's a lot in common there because the face huggers from Alien are parasitoids. Okay, so we only care about the first one. So that means that our function f, if we go just all the way back up here for a moment, this function f here was our fraction of the hosts that are not parasitized. Okay, so if we only care about the first encounter, then the fraction of our hosts that are not parasitized at time t is just going to be this p of 0. So we're saying the probability of there being no encounters is going to be the same as our fraction that are not parasitized. So we just need to substitute 0 in for I above. So we're going to have n to the 0. It's by e to the minus n. We have a 0 factorial, which simplifies down nicely to e to the minus n. And above, we've already defined what n is. N is the average number of counters per host, which is just A times by PT, where A is our searching efficiency, and PT is the density of parasitoids. Note that this doesn't actually depend at all on the host density, because this is per host. We're assuming that that's obviously over time, the parasitoid density is going to depend on the total number of hosts that are around. If there are more hosts, it can support more parasitoids, but that's an indirect effect. It doesn't directly, the number of hosts doesn't directly affect in a given time step your probability of getting infected. So there's no kind of like herding effect from the host that's protecting them or anything like that. It's entirely dependent on the current level of parasitoids. So you can see if there are more parasitoids around, this gets bigger, or if they are more efficient at searching for their hosts, if either of these things gets bigger, then you're going to have e to the minus bigger number. So this is going to tend towards 0. So the more parasitoids that are around, or the better that they are at searching, the fraction of hosts that are not parasitized is going to tend towards 0, as either A gets very large or P gets very large. Any questions so far? Yes.
So that HTPT equal to P0, right? So, well, it's if that PI I not equal to 0, what will happen?
So the reason that we're using, so this is just a general sort of Poisson process. Okay, this is if you for any number of, if we wanted to ask, what's the probability that a host encounters 2 parasitoids in, suppose these time intervals are a day. What's the probability that they encountered exactly 2? Then we would substitute 2 in here. If we wanted to know if it was 5, we would substitute 5 in there, and so on, whatever number we got. If we want to know the probability that they encounter exactly none, then it's going to be P of 0, right? And the reason why we care about this P of 0 is we're assuming that as soon as a host comes into contact with a parasitoid, it can't resist that parasitoid at all. So it doesn't matter if it comes into contact with 1, 2, 3, 4, 5, 6, 7, any number of parasitoids. At least as soon as it comes into contact with at least 1, it's going to be infected. Anything after that doesn't matter. So this F here is basically saying we want to know the probability that it encounters absolutely 0. If it encounters 1, it's infected, or 2, or 3, or 4, it's infected. It's only if it encounters 0 that it's not going to be infected. Yes.
Okay. The n to the power of 0 that we divide it by 0 and get
0 factorial.
Okay, 0 factorial.
So 0 factorial is equal to 1.
Oh, okay.
Yeah. So 0 factorial is equal to 1, and to the 0 is equal to 1 as well. Yeah, okay. Any other questions? It's good, ask questions. Okay. So we have an expression for our the fraction of the population that's not parasitized. So that means that we can write down our Nicholson-Bailey model. So our host population at time t+1 is going to be equal to its growth rate r times the density of hosts at time t times by the fraction that are not parasitized. We just work that that out as e to the minus apt on the previous slide. And if you recall in the general form of the model, we said that we're going to have C eggs produced that survive. And we're assuming as well that this is independent of the number of encounters, okay? So if, if they get parasitized by one parasitoid, they will produce C eggs. If it's two, they'll still produce C eggs and so on. So we're kind of assuming that there's a limit to the number of eggs that can be produced from a host. Being infected by two parasitoids does not change the number of eggs that are produced, okay? So there's a finite amount that can be produced and that's fixed for infection. So our equation for the parasitoid density is going to be C, the number of eggs produced per host, total number of hosts, and the fraction of hosts that are parasitized. 1 minus e to the minus apt. Okay, I think as it's a Monday morning, I don't want to wake you guys up. I want you guys to have a go at finding the two steady states of the model. Okay, so this is a little bit challenging. If you remember, we want to find a pair of values h star p star such that we have h star is equal to r h star e to the minus ap star. P star is equal to ch star. That's by 1 minus e to the minus a p star. Hope you guys remember how to work with logs. Okay, have a go at that, and I will walk around and answer any questions you guys might have. Okay, in the interest of time, I'll start working through that. But this is quite a good one to have a go at doing in your own time if you're not 100% sure if it's okay. It's good practice. Okay, so what do we know? From this first equation here, h star is equal to rh star e to the minus ap star, sorry. We know that h star must equal 0 because it's on both sides, or we can divide by h star, in which case we'll have 1 is equal to r e to the minus a p star. We can rearrange this as log of 1 over r. So divide both sides by r and take the log. That's going to equal minus a p star, which we can rearrange by dividing by minus a as being p star is equal to minus log of r. Sorry, log of 1 over r, getting ahead of myself here, divided by a. And then using this identity up here, we've got minus log of 1 over r. That's going to be equal to log of r. So this will just be 1 over a times by the log of r. And this is only realistic for r greater than 1. Okay, and we said at the start we're going to assume that r was greater than 1. Otherwise, the host population dies out, and you can't get this non-trivial equilibrium. You just have this trivial equilibrium. Okay. Okay, so let's think about what happens now if h star is equal to 0. Well, we're going to substitute it into this second equation here to find the value of p star. Okay, we see that if we set h star is equal to 0 here, the right-hand side is going to equal 0. So if h star is equal to 0, p star is equal to 0 as well. This is just our trivial equilibrium. Biologically, this makes sense, right? It was always good to, if possible, think back and think biologically what is going on here. So, for example, this one is only realistic when r is greater than 1, and we know that the population, the host population, cannot grow unless r is greater than 1. Okay, so that makes sense here. There's no hosts. There can't be any parasitoids. It would be weird if we had some hosts, no hosts and some parasitoids, because what would they be laying their eggs in? Okay, it's always good to do like a bit of a sense check if you can. Okay, so that's one of our equilibria. Steady states. I mean, steady states equilibria can be used interchangeably. in chemistry, there's a bit more of an issue when it talks about steady states versus equilibria, which is why I try to not fall too much into the trap, because sometimes you'll see in textbooks that will talk about steady states. Steady states and equilibria, as far as we're concerned, are the same things. Okay. Okay, let's think about our other one. So if we have this one on the right-hand side here, P star is equal to, in fact, this one here, 1 over A times log of R. And again, we need to substitute this into the second equation. So it's going to have to appear here and here. We'll have 1 over A times log of R is equal to C H star times by 1 minus e to the minus A times by 1 over A log of R. These A's here are going to cancel. And again, we can use this identity over here. If I take the minus sign over to the other side, we've got a minus log of R. That's just going to equal log of 1 over R. So we've still got this 1 over A log R on the left-hand side. That's by CH star 1 minus e to the log of 1 over R. Rather than write out everything again, I'm just going to simplify this. We've got e to the log of something, so we're just going to have the thing in the brackets, 1 over R. So these are just our log rules. I'm going to put it straight in here just to save a bit of space. Okay, so now we've got everything in terms of parameters. It's still quite messy, but we can rearrange this to get H star on its own. We can write the bit in the brackets as R minus 1 over R. And then divide both sides by C R minus 1 times by R minus 1 and times both sides by R. So a little bit of messy algebra, but not too horrendous. This ends up giving us H star is equal to this R here times by log of R divided by A times by R minus 1. And I missed a C as well. It should be an AC R minus 1. So we have this is equal to this. I'm just rearranging to get H star. So multiply both sides by R, divide both sides by C times by R minus 1. You'll get R log R over AC times by R minus 1. So that means we have a trivial steady state or equilibrium at 0, 0, and a non-trivial. You often hear, I mean, sometimes I refer to this myself as a coexistence equilibrium, because technically if you are at those values, you will coexist. Sometimes I try to refer to it more as a non-trivial equilibrium rather than a coexistence equilibrium, simply because coexistence can make you think that tells you something about stability. Okay, but we don't know anything about stability at this point. So a non-trivial equilibrium, just worked out as R log R over AC R minus 1 and 1 over A log R. Yes. We don't have any other, we've worked out up here in the yellow equation that the only two values that satisfy this are H star is equal to 0 or P star is equal to 1 over A log R. Okay, so those are the only two values that satisfy the first equation. And then we substitute those into the second equation. And if H star is equal to 0, the only value we get out is P star is equal to 0. And then if we substitute P star is equal to 1 over A log R, the only value we get out is here. Okay, so there's only two equilibria. Okay, stability, we need to look at our Jacobian. In the interest of time, I'm just going to write this down. I'll leave it to you to check that it's right if you want to have a go at deriving it. So if r e to the minus AP minus AR H e to the minus AP, C times by 1 minus E to the minus AP, and AC H e to the minus AP. Okay, like I said, I'll leave that as an exercise for you to derive if you want to. If you just want some practice of how we get to Jacobians. Our non-trivial steady state, we're going to substitute in this. Again, this is a little bit messy, but if we do this, our P is 1 over A log R. So when you do that, this first term here is just going to go to 1. So our non-trivial steady state, that simplifies down nicely. So we just have a 1 in this top left hand entry. I'm going to leave top right as minus 8A times by H star. The bottom will have C times by 1 minus 1 over R. And the bottom right, AC H star over R. Again. We could substitute in the values of H star there, but we know that H star is going to be positive. Ultimately, we just care about whether this are trace and determinant positive and negative with relation to those jury conditions. But we can leave them here for now. I could substitute those values in, but it's a little bit messy, so we can leave it like that. So let's consider our jury conditions. Again, it can be shown, but it's kind of laborious going through all of this, that our first two jury conditions are always satisfied whenever our non-trivial equilibrium is realistic. Again, if you want to do this as an exercise, you can. It's a little bit algebraically involved, just to make sure it's clear. It's these two jury conditions here are always satisfied whenever our non-trivial equilibrium is biologically realistic. And that means that our stability is going to be entirely determined by the determinant here. If the determinant is less than 1, then it's stable. If not, then it is unstable. So let's have a look at our determinant. For stability, we need 1 to be greater than our determinant. What's our determinant? Well, product of the elements on the main diagonal is just going to be ACH star over R. ACH star over R minus the product of the elements on the off diagonal. So we're going to have minus times by minus. We're going to have plus ACH star again times by 1 minus 1 over R. And this bit in brackets, we can actually write as R minus 1 over R. And that means that we can pull out the front an ACH star over R, multiply that by 1 plus R minus 1. Okay, so all I've done here is I've rewritten this 1 minus 1 over R as R minus 1 over R, doing over one fraction, then taking out a factor of R from this second term, as well as this ACH star, pulling that all out the front. So ACH star over R times by 1 gives us this term. ACH star over R times by R minus 1 gives us the second term here. That's quite nice because these 1s cancel. These R's cancel as well. And we end up with just ACH star. We could substitute in our H star now. What was our H star? Let's just go back up here to find it. We had R log R over AC times by R minus 1. So we have AC times by R log R over AC times by R minus 1. So that's just substituting in our H star. Now we've got A's and C's on the top and the bottom. I've missed off an R as well here somewhere. Yes, sorry, this R here I've left in when I should have. See, I had an AC. Oh no, we still have an R log R. It's all right, I've gone one step ahead of where I was in my notes. Okay. And we know that this is going to be positive for one thing because r is greater than 1. But we need it to be less than 1. So what we can say is equivalently, we require log of r, so log of r, h of r. Turns out that when I write log of r, it looks very much like h of r in my notes. Let's define a new function h of r. And this is just going to be taking this. Let's see, how's the best way to do this? What we want to do is we want to ensure that this inequality up here is greater than 0 and less than 1. So if we define a function h of r, which is equal to r minus 1 minus r log r, want this to be greater than 0 whenever r is greater than 1. But if we think about the value of what happens when r is at its minimum value, so we're assuming that r is always greater than 1. What happens if r is equal to 1? That'd be just at the threshold where the host is able to survive, okay? If we substitute 1 into here, we're going to get 1 minus 1 times by log of 1. So that's equal to 0. Okay, so that's the first piece of our puzzle. It'll become clear, hopefully, what I'm doing in just a moment. If we take the derivative of this, we're going to get 1 minus, by the product rule, we're going to get a log of r plus r times by 1 over r. These will cancel. And so we end up with the gradient being minus log of r. R is greater than 1, so this is always negative. So what this is saying then is that this inequality here, this value of h, when it reaches a maximum of 0, when r is equal to 1, it's always decreasing for any r greater than that. So it can never go above 0. So this inequality can't be satisfied. So h of r is less than 0 for all r greater than 1. That means our jury conditions are violated. And so this non-trivial equilibrium is unstable. I'll say as well, this is quite an involved example. I wouldn't expect you to do something quite as complicated as this in an exam. But I've gone through it here just to demonstrate that even in these more complicated examples, and in this quite famous model here, that we can show that the jury conditions are violated. Okay, so don't worry if you're not able to replicate this yourself. I wouldn't be expecting you to do something quite so complicated in an exam. So what does all of this mean then? Well, I put some code on Canvas for you to numerically explore what's going on. So have a go at playing around the parameters with that and starting relatively close to this non-trivial equilibrium and seeing what the outputs look like. So what we have is we haven't looked at the stability of our non-trivial equilibrium, but our trivial equilibrium, but we know our non-trivial equilibrium is unstable. Is an unstable node? Is it an unstable spiral? What actually happens when we try to do this? So have a go at using the code on Canvas to numerically explore and see what all of this means. Okay. If there are any questions, I'll stick around for a few minutes. If not, I will see you on Wednesday. Wednesday is going to be a review lecture, going over basically everything, or most of the things that we've done with species interactions. I'll actually be talking about it in terms of an age-structured model, because we haven't really talked about age-structured models, but the same ideas of, you know, finding equilibria, stability, and all of that, they apply in structured models as they do to species interactions. Okay, so we're going to go through that on Wednesday. It's a good opportunity if you have any questions about any of the stuff that we've done, basically from our resource competition lecture forwards. That's a good time to ask those questions. I won't be, when we're doing our disease models, we'll be going back and using some of the techniques we've used before. Sometimes I might just sort of skip forward ahead to say, you know, these are the equilibria or this is the stability, rather than going through all of the process every single time. Okay, so if you're not sure about the process or anything, Wednesday is a good opportunity to ask. In future, I'll often be skipping forwards. Okay.